This is 6.4 Exponential Growth and Decay. So exponential growth is when a quantity increases by the same factor over equal intervals of time. So over a year, something could increase by double. So it'd be multiplying by 2, so it increases by the same quantity over equal intervals of time. Every month, every year, every week, something like that. So here we have an equation for how to find exponential growth. So we would have y would be the final amount, a is the initial amount, we have 1 plus r, and this is considered the growth factor, r represents the rate of growth, and t is time. A must be greater than 0, and r must be greater than 0. The first attendance of a festival is 150,000. The attendance y increases by 8% each year. Write an exponential growth function that represents the attendance after t years. So, I'm going to be using the function y equals a plus a times 1 plus r to the t power. And I don't know y. I do know a, and a is going to be 150,000. And then I have 1 plus r, so it tells me it increases by 8%. 8% needs to be written as a decimal. So I move the decimal spot 2 spots to the left, and now I have 0.08, and that is what my function would be. Part B says how many people will attend the festival in the 5th year. So this means t equals 5. So in my function, I replace the t with a 5, and then calculate. So that would be 1.08 if I simplify this, 1.08 to the 5th, find that number, and then multiply by 150,000. So I have 220,399. Rounding to the nearest 1,000, that's 220,000 people. We also have exponential decay, and that would be when a quantity decreases by the same factor over equal intervals of time. The same function will be used, but instead of adding r, you subtract r. And this time r must be between 0 and 1, so it cannot be negative and it cannot be greater than 1, and a must be greater than 0. So we're going to determine whether each function represented is exponential growth, decay, or neither. So if I have this table of values, I can see how much are they changing from each y. And for each one, I'd be dividing by 5, or I could multiply by 1/5. Multiplying by 1/5 is the same as dividing by 5. So this is a ratio, so I know that's going to be exponential, and the numbers are getting smaller, so it's decay. So it's exponential decay because we have a constant ratio. Now for this one, I see that my y values are increasing, so I know it's going to be some kind of growth, but is it exponential? So I see how much does it change. Each one increases by 15. So you add 15, so this is a linear function, and it is not exponential. Here, I can see that each y value will multiply by 2 to get the next. So since this is multiplying by a ratio, this is exponential growth. If I give a equation, this would be this middle part here in the parentheses is taking that 1 plus r, and they already simplified that. So it is larger than 1, which means that it will be exponential growth. Here, this number in the parentheses raised to the t power is less than 1. If it is less than 1, it will be exponential decay, because this would be 1 minus r, and r would be 0.05. 1 minus 0.05 is 0.95. They just simplified that already. So if you have larger than 1, growth, less than 1, decay. But sometimes they're not always given in just this form. Here I have 1.2 times t to the t minus 4. So I need to rewrite this to have just a regular t. And so I'm going to use my property properties of exponents to rewrite this and simplify. So I would have 1.2 to the t over 1.2 to the 4. I can figure out what is 1.2 to the 4th power, and that is 2.0736. I can round that, and then whatever, I need to write this as something to multiply. So if I do that, I would be multiplying by this number, 1 over this number. So this is a little incorrect. So then in this form, I know that this is greater than 1. It'll be exponential growth.